Hello, welcome back to the course on Audio Signal Processing for Music Applications. In the previous programming lecture, we talked about the HPR model, the harmonic plus residual model. That was the idea of modeling a sound with a harmonic and a residual component, and we talked about the implementation in the SMS Tools package. Now we want to go a step further and talk about the HPS model, the harmonics plus stochastic model. So now we are modeling the residual that we obtain with the stochastic modeling approach. So we obtain a harmonic and a stochastic representation of a particular sound. So the diagram, the block diagram, is very similar. The whole thing for the analysis is the same until we obtain the residual spectrum of x, xr of k, and then instead of just going and summing it with the harmonic component, what we are doing is approximating it with an stochastic approximation, so by smoothing the magnitude spectrum, and then the synthesis is done by generating random numbers for the phase and combining it with sort of an interpolated version of this approximation so that we generate a complete spectrum, and this stochastic spectrum can then be added back to the harmonic component. The great advantage of this stochastic approximation is that now we are more flexible. We can do many more things on this representation apart from being much more compact. This stochastic approximation reduces the amount of information that is required to reconstruct the signal. So apart from being a compact representation, it's more flexible, and we'll be able to do quite a few things with that. So let's start from the same code that we looked at in the last lecture, which was this code in which now I changed the sound. Now I use a flute sound, but basically it performs the harmonic analysis by taking FFT and detecting the F0, so it performs the harmonic analysis steps, and then it synthesizes those harmonics and it subtracts them from the original signal. It recomputes a spectrum of the original signal with the same window size and type than the one that is in this generated sinusoidal spectrum. So we need to multiply by a Blackman-Harris window, and we need to choose the window size that was the same than was used for the sinusoidal synthesis, and we can then subtract the harmonics from the original signal and obtain the residual. And now in this lecture, basically we focus on the stochastic approximation of this residual, and these three lines are doing that. So the first is we are converting it to a dB scale. So we are converting half of the magnitude spectrum to a dB scale, and we obtain a new magnitude spectrum. And then we call this function called resample with this magnitude spectrum, and of course with values that are above a certain threshold. And we are converting it to a shorter array, and the size of this new array is the size that we started from multiplied by stoch f. And stoch f is our stochastic factor approximation, basically is our smoothing approximation or downsampling factor. So basically it means that the output array will be 40% of the original spectrum. And then we are upsampling again to the size that we started with in order that then we can do the resynthesis. So in fact, resample can be used both for downsampling and for upsampling, and it uses the DFT approach. So let's talk a little bit about that. So we can go to the documentation on the resample function within SciPy. Okay, So this is the documentation. So it takes an array, it takes the size of the output array, so either less or more, so you can downsample or upsample. And well, there is some optional arguments also that allow us to give a particular window or to give a more multidimensional array and process only part of that. And since Python, of course, is all open source, we can also see the source code of this function. And as I said, well, a resample uses an Fourier-based approach to do downsampling and upsampling. And what it does, it performs first the FFT of the input signal. Then it will basically cut the spectrum or append samples, depending if it's upsample or downsampling or upsampling. And then once we have recomputed a longer or a shorter spectrum by cutting or appending zeros, we perform the inverse FFT. That's a quite straightforward, simple way of performing interpolation or downsampling or upsampling. Okay, so we go back here. So this returning for the first resample, we will return less samples, and then afterwards we will convert it to this upsample version that will be a smooth version of the spectrum we started with. Let's run this so we can see how that works. So let's run test 4. Okay, and now we can plot the original spectrum. So MXR is already the dB version of the spectrum and half of it. Okay, so this is our residual spectrum. And then if we plot on top of that the stock EMF, that's of the same size but a smooth version, because it's the result of having first downsample and then upsample with interpolation. Okay, so as you see, we are very much, in fact, if we zoom in into any of these regions, we see that the green line is the smooth version, but is of course is smoother than the original one, but it follows quite well the original signal. So let's change the stochastic factor of 0.4 and let's put maybe 0.1. Okay, so then that will be a stronger smoothing factor. And if we save these and then we compute it, okay, now we plot again the original residual spectrum, and now let's plot the smooth envelope. Okay, and this clearly shows the smooth envelope on top of that, and it's much smoother than before. Okay, so that's basically what the stochastic approximation does. And if we now go into the HPS model code of the SMS tools, well, we'll see the analysis function, the synthesis function, and also one function that does analysis and synthesis at the frame level. And the analysis, for example, is basically the same than for the HPR model. We only add one input parameter, which is this stock F, the factor, the smoothing factor. And then in the analysis, we first perform the harmonic analysis, then we subtract the sinusoids from the original signal to obtain the residual, and then we run the stochastic model anal, the one that we already discussed when we talked about the stochastic model. So we just, the stochastic model receives the signal, the residual signal, and it has the hop size, the same hop size that we are using. And now the window size that we use for the stochastic approximation is just twice the hop size. So in fact, the stochastic approximation does not require big windows. In fact, it's all the other way around. The smaller the better, so we can capture time information, the stochastic components, the residual components, the time information, the attacks of the nodes, etc., are most critical. So the smaller the window, the better. So in fact, if H many times is by default like 128 samples, here we are using windows of 256 samples. So we will be computing an FFT of 256 samples and approximating that. Okay, and of course then we return the harmonics, and instead of returning the residual, we return these envelopes, this sequence of envelopes that we are computing. And in the synthesis part, well, it's a similar situation. We synthesize the sinusoids and then synthesize the stochastic component using the stochastic model synth that also we talked about. So from these envelopes, we can synthesize the stochastic component. And the function that puts it all together, there is this HPS model function that includes analysis and synthesis using the harmonic plus stochastic model. So it has some parameters, default parameters, and then it performs the analysis and it performs the synthesis, and in the process it plots certain intermediate values. Okay, so let's go to the terminal, and now instead of running the code or running the code by calling the file, we can also run the function directly, and that allows us to be able to change the parameters. So if we import this function, the HPS model function, okay, now we have imported, we haven't executed it. Now, we better to just import it with a given name, for example, HPS. Okay, and now we can call HPS and the function within HPS. So within this file, there is this function main. So we can just call main. And here now we will be able to change the values of these parameters. So let's just get the values by default. Okay, so this computes this analysis and synthesis of this sound, of this sax phrase with the default parameters. And now, if we can play around, so of course we could use the interface that we have been showing in the demo classes, but here it may be sort of more intuitive in terms of understanding what is going on and being able to go deep into the code to just replace parameters here. So for example, now if I want to change the threshold and make it a smaller threshold, instead of minus 100, let's put minus 40, then we will run the same code but changing the threshold. And of course, changing the threshold has meant that it found only few harmonics. In fact, it considered everything stochastic, and in here the stochastic representation is the one that is more prominent. Okay, and you can change any parameter. You can change the sound, for example. Okay, let's we can change the sound file, or we can change the minimum duration of the harmonics, etc., etc. So no need to explain that anymore. Basically, we can just execute it in any way we want. Okay, and that's all I wanted to say. So this is basically an extension of the harmonic plus residual model, and we have seen how it works. So basically, this is the most complex model that we're going to see in this course, and all the others can be understood as kind of related with this one. So if you understand this model, I think it's a good way to understand a lot of the things we have been talking about. So that's all for today. So I hope to see you next lecture. Thank you.